Hello everybody and welcome back to the Quantum Classroom and to our Careers in Chemistry series, where I'm doing interviews with leading researchers across all fields of chemical sciences to give you an insight into what working in the chemistry industry is really like. And today I'm delighted to be joined by Associate Professor, Leader of Actuate Lab in the Bernal Institute here in UL, and the SFI Early Career Researcher in 2023, Dr Sarah Guerin. Thank you for joining me.
Thank you for asking me.
Okay, so my first question is, will you just, I suppose, introduce yourself, tell us about your research and what exactly is that you do?
Yeah, absolutely. So as you hinted at, I'm an associate professor in the Department of Chemical Sciences here in UL, and our research group, which currently has about 15 people, spans physics, chemistry, engineering, loads of different aspects of science. In terms specifically of chemistry, what we do is something called crystal engineering, where we work with crystals that have essentially cool properties. They can be used as sensors and actuators. Some of them convert light into energy. Some of them convert force into energy. Some of them just hop around a lot. And crystal engineering, we look at those materials at the nanoscale to try and predict and understand and design those properties in these materials. So what chemists can do is essentially work with the building blocks of these crystals, which is molecules, and arrange the molecules in the way that they need for these properties to work.
Okay, cool. So I suppose you kind of hinted that already for my next question. I suppose then, why is the research you carry out, why do you feel that it's important? And then I suppose then what impact can it have once it's hopefully successful?
Yeah. So far so good. But yeah, the big thing for us is, say, the main property that we look at is something called piezoelectricity, where you're converting force into useful electricity, or vice versa. You can pass electricity through the material, and it will actuate, it will move. So the big thing that we're focusing on is sustainability. So I just said that all of our crystals are made of molecules, but that's actually quite rare. And the materials that are used for these applications currently are polymers or plastics, or ceramics, which are a particular type of chemistry called perovskites. But they contain elements like lead, barium, bismuth, niobium, all of which are things that need to be dug out of the ground, which means they're scarce, and it means there's a lot of environmental and human impact to that. And all those elements are very toxic when you dispose of these materials and sensors and actuators. So when we work with molecular crystals, the majority of those materials are the ones that we focus on are eco-friendly. So the joke that I always make is that we can eat some of the samples in our lab. They're kind of supplements, things like that you could buy in Holland and Barrett, proteins, peptides, collagen, that kind of thing. Where you can crystallize it, it will have this property where it can interconvert force and electricity, but it's completely eco-friendly and sustainable and cheap. So our goal and the impact we want to have is to make these crystals good enough so that we don't have to use any of those ceramic materials anymore that are damaging the environment currently.
Cool. So there's like a big impact that it can have.
Yeah, like there are billions of lead-based ceramics currently, a couple of hundred in this room, I'd say, that have lead in them that will be chucked into a landfill if they're disposed of incorrectly, which then leaches those things into water supplies, things like that. So like,
is this like something that can happen in like the near future, or is this still like a down the line kind of thing?
That's a great question. The way that we're doing it in my group and the way that we got funded through the EU is to accelerate it. So when I said we're doing a bit of everything, we're also doing a bit of everything at the same time. So we have people who are running very cool computer simulations to help discover these materials faster. We have people who are just working on growing these crystals in a way that makes all of these properties stronger. And we have engineers who are turning these materials that you wouldn't expect to find in your phone or your laptop into an actual device that can be used. So because we're doing all of those things simultaneously, we're aiming for 2030. To really have them at a commercially viable level. And this year is the first year that we have industry partners working with us on the ground to get these into medical devices on that same timeline, which is exciting.
Yeah. Who are the industry partners?
I don't know if I can say who the industry partners are.
It's top secret.
There's a lot of NDAs involved in these things. But yeah, our goal was to get kind of as many multinational particularly medical device companies in Ireland, because there's such a good landscape for that, involved in the project at this point, so that when we do get to technological maturity, we have these partners ready to go to buy or license or use these materials. And we're designing them in a way to make it as easy as possible for industry to just take out that kind of toxic element component and put in our eco-friendly crystal component.
Cool. So I guess next then I might turn to you personally and ask, what has your journey been so far? Like, how have you gotten from, the way I phrased it before was like, how have you gotten from, I don't know, wherever it was that you started with science to this point now where you are?
Yeah, well, it's been very UL centric, which is why I think my face is outside the building that we're currently in. But I'm from Kerry myself, so I'm from Tralee, which is about 2 hours down the road. And I think you get a lot of those stereotypical science stories about, I made circuits when I was 6 and I looked through magnifying glasses when I was 2. And I think I was generally, I was just a bit of a, I don't know, what's the word? Teacher's pet.
Yeah.
Kind of liked all of the things.
I get that.
I liked science, I liked English, I liked maths. I just, that kind of way. By the time I got to the Leaving Cert, I mean, the joke I always make, because it's now my career, is that my best friend chose physics and applied maths. She was the only woman who chose physics and applied maths, so she dragged me along to those classes. And then here I am, 15 years later, building or running a kind of a world leading research team, which is kind of surreal. But if my music teacher hadn't been so rubbish, and if my physics teacher hadn't been so excellent, then I might have chosen the path that I did. So I trained in applied physics here in UL. That was my undergrad. And we did a lot of kind of electronic sensor-based stuff, but also kept up a lot of the chemistry. So I had done chemistry and physics for the Leaving, and I wanted to keep both of them as much as possible. Yeah. And then I stayed on here in UL with Professor Damien Thompson to do my PhD, kind of straight out of the undergrad. Finished that in 2018 and then worked in kind of pharmaceuticals for a while. Because the computer models I mentioned, they can be used for pharmaceuticals. So if we can model collagen for, those functional device applications, we can model collagen for pharmaceutical applications as well. And then COVID happened, and during the pandemic I wrote this big EU grant to take on all of the challenges that I mentioned around sustainable energy conversion, and that was awarded just before Christmas Day on 2021. And now the group is 2 years old and has 15 people in it. And the science I came up with in my brain when you couldn't, leave the 5 kilometre radius of your house is working.
And all's going well.
Yeah, so far so good, as much as I can.
So I suppose that was going to be my next question, was then what led you to your current area of research? But then I guess it was COVID and the things in your own head.
The grant was COVID. I mean, I think a lot of people's research naturally, when you do a PhD, it's generally your supervisor's research. You pick it for the supervisor, you vaguely like the field that they're in. And then if you want to go the route of academia and establishing yourself, 9 times out of 10 it has to come from that in some way. So Damien Thompson was my supervisor on the modelling side, where he does all this kind of cool computer simulations of all of these things that are made of molecules that can do fun things. And then it was Tofal Saeed in the Department of Physics who worked in this piezoelectric space and proteins that were piezoelectric. And then in my PhD, through trying to work on those two things at the same time and the vision they had, discovered that these particular type of molecular crystals could have technologically significant piezoelectricity. And then that became my niche. That I kind of split off then to work on that avenue.
What's it like leading a research group at such an early stage in your career? Because you're only, what was it, you said 6 years out of a PhD?
So it's been fast
Yeah.
and intense. I think I knew I wanted to run a group, and that's why I wrote the big grant. And, you know, part of that grant was I need a lot of people to do these things. So it was what I wanted and expected from the route that I chose. I like event management. I always said I'd be a wedding planner if I wasn't in science. So I think organising things on this scale is also something that I knew that I'd like, and that I'd be relatively good at.
Yeah.
Again, so far so good. It's been fast. You need to talk to a lot of people. You need to ask a lot of questions. You need to do all the stereotypical things of like not be afraid to fail, not be afraid to tell people you don't know what you're doing.
Yeah.
And yeah, you have to kind of get out of the mindset of what if I mess this up or what if I do this wrong. You really have to think on your feet and ask all of the questions, and that goes from the scientific to the how do I buy this thing in this university for my lab. So it's and it's having good peers. I have a lot of people in UL who got grants kind of the same year I got grants, and you have social activities where you go in and talk to people and vent about the challenges. But no, if I went back in time, I wouldn't change it. It has been an absolute roller coaster over 2 years, but looking at it now when things are kind of starting to settle down, and everybody in the group has become this like ecosystem of science, and are kind of working more independently, no, I wouldn't change it at all.
Okay, cool. So the group obviously, as you said, has many ongoing projects, and the one I'll talk about, seeing as you mentioned crystal engineering, is the Crystal Clear project. So could you talk a bit about, I suppose, what that project is, what its goal is, and then I suppose the impact it can have when it's finished? Yeah,
I mean, another thing that I love as a scientist is public engagement and outreach and involving everybody in science. And there's a certain branch of science called citizen science where you can, I suppose, use it's like crowdfunding the labour of doing science more than the cost of doing science, where if you can get a lot of people to do research across, for us it's all of Ireland, you can collect a lot of meaningful data from that and involve the public in your research. So a big challenge with these crystals is because they're like natural biological materials. When you grow them, we try to grow them as polycrystalline materials, which means you have a little kind of 2 centimetre square of a metal, and we have to grow these crystals on that piece of metal, and every single time they'll grow in a different way. And what we want is for them to grow them in exactly the same way, so that a particular face of the crystal is touching the metal every single time that we grow them. And that's very hard. And there's a student in my group, Krishna, and her whole PhD has been developing a methodology to do that. And the second that she kind of nailed that recipe in terms of how much of each thing do we mix together and the temperatures and all of that kind of stuff, we said, let's roll this out and let's really see how accurate this recipe is if 100 people across Ireland do it in their homes. So what we did was we worked with SSPC, which is the Pharmaceutical Research Centre here in UL, because they do a lot of these projects with a lot of these kinds of materials, and we made these kits. Because the good thing about being able to eat your samples means that people can make them in their kitchen and their living room without any kind of chemical dangers that you could associate with crystallization. So we made these little kits, and we sent them out to 100 people around Ireland. We've given them these slightly rigid instructions as to how to make these materials and a big feedback form to send back to us. And it takes about 3 weeks for the crystals to grow. So they make them at home, they grow the crystals in the way that we've asked them to, hopefully, and then they send them back. And we have an undergraduate student, Hannah, who's here for the summer, and she's going to be characterising all of the samples people send back to us to see the variability in properties based on this recipe that we made. So again, when we look towards like medical device companies and industry, every time you make something, it has to be very, very, very similar. So we're testing that at the biggest scale, where we have, everybody from, I think we have the ages of 4 to the ages of 74 making these crystals currently in the country. Are we going to get huge variability? What's the standard deviation? I suppose all the things we learn about in first year undergrad. What's the Gaussian distribution of our properties, and really pushing it to the extreme in terms of reproducibility of this method that Krishna made. So we're excited. It could be absolute chaos, but that's also data. So we're excited to get them back and see what people have done with it.
Cool. So like, what was what's the process for someone of growing a crystal in their house? Or is that top secret? No, absolutely not. No. So essentially what we do is we have a powder of particular amino acid, so it just looks like a white powder on the bench. We have people boil water in their kettles, and then we've timed exactly
how many seconds it takes boiling water to cool to 70 degrees at, using a normal kettle at home. So people boil the water, they let it cool for the amount of time that we know that it will be 70 degrees at, so we don't have to give people thermometers. And then they mix the water and this powder together. They add salt, scientific grade salt that we've given them, which makes the crystal grow in the particular shape that we want it, with the particular properties. And then we've given them what are essentially, or what are literally, are silicone molds that you kind of make sweets in. Those kinds of, so they're like disc-shaped sweets. You pour the solution into those molds, and then as the crystals grow, they take on the disc shape, like you're making sweets or macarons or one of those things. So what we'll get sent back from them is these crystalline discs that they've grown in the molds. They send it back to us in the molds because it's very hard to pop them out. We're trying to minimise as much damage as possible through posting all of these things around Ireland. So essentially you have to kind of leave them in a relatively quiet, relatively warm place. We kind of did loads of tests of this with staff in UL. And we were all trying to do it in our back kitchens in January. And the colder it is, the longer it takes crystals to grow. So we're happy that we're doing it now in July, where people can kind of leave it wherever they want. So they leave and wait, and they send it back. And we'll see how disc-like the things we get back are.
That's cool though. I know I'm talking about chemistry. I'm going to delve a little bit into physics, which I hope Luke won't mind. But one thing that you, as far as I'm aware, started in UL was the Sophia project, which is all about promoting women in STEM and physics in particular. Will you talk a bit about, I suppose, the Sophia project and I suppose the importance for you of promoting women in STEM? Yeah,
absolutely. Didn't start it. Just for people listening, no, but I've run it for the past couple of years. It was started by Dr Grania Walsh, who's no longer in UL. She's working for the Irish Research Council. She used to run the Science Learning Centre here in UL for students in STEM. And she started this project with the goal of generally increasing uptake of physics as a leaving cert subject, because it's one of the least, I suppose, has the lowest numbers of uptake currently, but to do that through equity and equality in physics education and showcasing underrepresented groups in physics. And the goal was always to get rid of the kind of Sheldon Cooper, Einstein, that kind of visual that people have around physics and science. And it was hugely successful. It was Grania and Agatha Lynch, who's a researcher here in the EpiSTEM Research Centre. She's done all the actual, I suppose, social science and data collection of the impact of the project to date. But essentially what it is it's a school workshop where undergraduate students go into primary and secondary school classes, and they give a 40-minute to an hour workshop. Very practical, very hands-on, a lot of explosions, a lot of Alka-Seltzer rockets, a lot of colourful things, to break down the perception that physics is all about maths and is very kind of stoic and theoretical physics and writing equations up on a board, and to break down those stereotypes about who can do physics and who has done physics as well, which I think is key. So we showcase a lot of, as I said, women, LGBTQ members of the science community from history, but also currently in active research. And then we do surveys before and after to see if we've changed people's perceptions of physics in that time, which it's amazing to say that you actually do. It only takes an hour to kind of really, to challenge people's beliefs that they have about these things. But it's rare to see such impact in such a short amount of time for a project. We have a number of undergraduate women who've come into the physics department in UL because they had a Sophia workshop in their secondary school in the Limerick area. And the group that are coming into fourth year now, just gone, is the largest physics class size we've had, with 50% women for the first time, which we've seen on the smaller end, which you can say 50%, but sometimes that means there's only 6 or 7 or 8 students in the class. This was 40 to 50 students with 50% women.
Yeah.
And many of those had a Sophia workshop and are now delivering Sophia workshops, which is also really lovely.
Okay.
So we started to make almost an intergenerational tier of the programme. But yeah, we work very closely with teachers, work very closely with the Academy of Children here in UL, which specifically targets Dept primary schools, to get them more involved in science and see themselves doing science. And it linked in nicely to the Crystal Clear project as well. A lot of, the demos that we did to test this out, we did with schools who either work with the Academy of Children or who have done a Sophia workshop, who tested out these methodologies for us to make sure that they could be scaled up and sent to people's houses. Yeah.
Cool. Where, or maybe this is a bit too philosophical, but like, where do you think that whole stigma around physics being all mathsy or being like too hard comes from?
Do you have 5 to 6 hours?
Go for it.
Again, you can get very, very philosophical. And I mean, we're doing this interview, 24 hours after, the first potential black female president of the United States, decided to announce her candidacy. I think it's become a weird, what's the word? Overused phrase, which is a weird thing to say. But I do think it's patriarchy. I do think it's capitalism. I do think it's the existential structures that we've built in our society, because when you look back on the scientists that we do view as hugely important and who were hugely important to various scientific developments, but even in the past couple of years, we've seen, I suppose, the cancel culture of Schrödinger, a lot of things about Einstein and how his wife was potentially involved in a lot of that research and wrote a lot of those papers and research without any acknowledgement or of that kind of thing. The invisible labour of women and of female scientists. And that's why I think it's important to highlight that we're not saying, there's a lot of, again, phrases where you say like, underrepresented groups in science, but a lot of the time it's hidden groups in science, where it has, women have always, or obviously some women have always wanted to be scientists, some men have always wanted to be scientists. Yeah. They'll always be the people who want to do science. And it's more promoting and highlighting that that's always been the case throughout history, but that they haven't gotten the plaudits as a lot of the, again, I suppose, Nobel laureate winning or the scientists that we have in our history books and our science books. Yeah. But yeah, that's kind of the stereotype. It's the straight white man writing equations on a whiteboard. That seems to be what society valued for a while, what they needed science to look like, and what they needed science to be. And yeah, it's surreal to be a woman at this time, still having to talk about women in science while wearing Taylor Swift friendship bracelets and things like that. It's more about humanizing science and getting rid of the idea of a genius, I think, is the big thing. Yeah. People associate science with genius. And that's been the biggest thing that we've tried to change, where it's like, no, you like it and you work hard at it. And those are the only two things. Same if you ask me to draw something. I think people who can draw and paint are geniuses, and I couldn't do that. And that's how some people feel about maths. And what I've loved as a lecturer has been breaking down this perception of, I can't do maths. Yeah. And maths is impossible. So yeah, there's a lot of big kind of societal beliefs that exist that we're trying to break down. Yeah. And it's really interesting to delve into the history of where those things came from in order to change them now, to get as many people who want to do science doing it. Yeah.
Cool. Okay. I suppose I look to the future now. Where are you going from here? What does the future have in store?
Like I said, it's been a roller coaster of getting to this point. So it's surreal now that I do have to start thinking about what's next. I love leading a big group who's doing a lot of science, I think. And being told that the culture we've created and the research team that we have is amenable to all the things I just talked about, where we get people in who mightn't have done a PhD, who mightn't have gone into science, who feel comfortable in the space we've created for people to do science, is really nice. So outside of the actual technological future that I want to look at, that's something that I always want to have, is a safe space for people to do advanced, important research. No matter who they are or their background or what they've done in their lives so far. So that's number one. Number two is what I said. I think seeing this in a medical device for the first time is going to be hugely impactful, the materials that we work with. And yeah, it'll be very surreal to see it go from me as a PhD student to potentially it being something. I don't like saying something that's being sold, but I suppose that's the only option now to get things into things. But yeah, to see this become commercially viable, and to see the people in my research group be the people that make that come to fruition, is something that I'm excited to see. But yeah, in terms of what I think the future is going to look like for science, again, I hate saying AI and machine learning, but I think ethical and scientific use of machine learning for science as opposed to ChatGPT and data centers and that kind of stuff. I think the scientific use of it in terms of data and nanoscale engineering, I think is going to be really exciting, and I think it's something we're going to move into as regards that, like engineering crystals at the molecular level. Is going to be really cool. I think that's going to be more impactful in the next couple of years. And that's pretty much it. Getting my first dog. That's something in the future. That's on the list. Something big and fluffy is the plan. But no, I think that's it. I think making our materials commercially viable, keeping that safe space for people to do research, and hopefully keeping this level of enthusiasm both in myself and in the people who fund research for kind of sustainability and actually making an impact for changing how the next 50 years are going to look. Across the world is important.
What keeps you motivated? Is it that like wanting to have an impact?
Sometimes just to give, I suppose, something a bit different, because again I think we hear a lot of things about I'm changing the world and that's cool, and it absolutely is. Again, it's very cool to be doing something that could have an impact, that could reduce climate change and could do all of those things. But in terms of something a bit different, what keeps me motivated is forgetting about science for a bit. I think at this point in my career, and again all the stuff we talked about like underrepresented people in STEM, it's about kind of maintaining your personality, and it's about doing lots of things outside of the lab and as a person, and not losing yourself to, I can change the world and I, need to spend my entire life in the lab slaving away. That's what creates imbalances in science. And I think it's what motivates me is that it's my job and it's not my life. And to work very, very hard at what I do, but to not lose myself in all of the exciting stuff that we're doing. Is something that I find very important. So yeah, what motivates me is meeting my friends on the weekends, and I'm going to keep talking about Taylor Swift, going to Taylor Swift concerts, going to gigs. And again, I think that's contributed to the culture that we have in our group as well, where people work very, very hard, but I think a lot of them also play very hard. And it's remembering that it's not your job to change the world, it's just cool that it's your job to change the world.
Okay, 2 questions to finish off. If somebody is listening to this, hopefully, and thinking of either studying or pursuing a career in chemistry or in physics or in science in general, is there anything you would say to them?
Practically, please go talk to your lecturers in third year, because it's very hard to it's very easy to bring you into research when you talk to us in third year as opposed to talking to us in second semester or fourth year. Still obviously do that, it's very important, but if it's something that you're excited about, the sooner you articulate to people it's something that you're excited about, the more we can support you. Again, talk to people. I think it's much better now. When we were undergraduates, I think there was more of a divide or a fear in just going up and chatting to your lecturers, which I think is a bit better now. Talk to lecturers early, talk to people in science, do things like summer internships that are always available to people in UL and around the country. Tyndall and UCD and all the universities do great undergraduate summer research programs. And like I said, kind of work hard, make sure you don't have any inherent beliefs about your abilities that are holding you back. And I say that a lot of the advice that I give people about science is more like a therapy session than it is about any kind of scientific acumen. It is more of the kind of believe in yourself and believe that people want to help you achieve your goals, and especially in the academic space. The majority of your lecturers, I won't say all in case people have exceptions to that, But 90% of the lecturers I know and academics I know, all they want to do is do fun science, get people into science, and do exciting things, motivate people to achieve what they want to do. So yeah, let people know what you want, and let them help you get it. Yeah,
okay.
That'd be my advice.
One final question then. Obviously this is a Leaving Cert podcast, and as when this goes out, people will either be just starting 5th year or just starting 6th year. Any advice? Thinking back,
everything that you think is important now isn't going to be as important as you think it is, in a good way.
Yeah.
The stuff you love will stay around, and the stuff that's stressing you out will disappear into the distance. Focus on what you like to do and not what everybody's telling you to do. Again, sounds like a cliche, but just hugely, hugely true.
Yeah.
If there's any way for you, and maybe that won't be until you get to college, maybe that won't be until after college, maybe you can't take that advice right now.
Yeah.
But as soon as you can make the decision to do something that you at the very least can tolerate, but hopefully enjoy and love and are passionate about, the better. See the Leaving Cert as a step to the things that you want to do. Nobody asks you your Leaving Cert points once you get to college.
True.
So do very well, work very hard, but if it's something that is stressing you out right now, know that there are loads of other avenues to achieve what you want to do, and as I said, talk to people about your problems, talk to people about what you love, and lean on the people, both adults and peers and friends around you, to get you through this tough time and to get you to where you want to go in the future.
Okay, perfect. Sarah, this has been a fascinating conversation and very interesting. Thank you very much for your time.
Yeah, thank you for the opportunity.
If you want to learn more about Sarah's research, there'll be links in the description of the podcast for you to do exactly that. And if you want more from the Quantum Classroom, you can listen to us on Spotify or wherever it is that you get your podcasts. And you can also follow us on Instagram or TikTok. We are at the Quantum Classroom Pod. Thank you for listening, everyone.